Good day everyone, welcome to our presentation. Today, we will talk about the chemistry of water. But first, let me explain what is chemistry of water. So chemistry of water is fundamental to life and many chemical processes. Water is not just the most abundant substance of Earth but also the foundation itself. Understanding its chemistry gives us insight into its vital role to nature, our bodies, and the environment. In this presentation, we will talk about three aspects of water's chemistry. Number one is the properties, classification, and the source of water. Number two is the reaction of bases and acids in water. And the last one is water pollutants and its treatment. Let's dive in the fascinating world of water's chemistry. Let's start with properties, classification, and sources. We'll delve in what makes water unique, how it is classified, and where we can find it in our world.
Now, let's talk about water sources. So, water is essential for life and is found in various natural sources on Earth. These sources can be categorized based on their location, type, and the method of replenishment. So here are the 5 primary water sources. Number 1, surface water. Number 2, groundwater. Number 3, rainwater. Number 4, glaciers and ice caps. Number 5, atmospheric water. So let's talk about number 1, surface water. Surface water refers to the water found in rivers, lakes, reservoirs, and ponds. These sources are the most visible and commonly used for human consumption, irrigation, and industrial activities. They can be replenished through rainfall, snowmelt in cold countries, or by inflow from other bodies of water. Next, let's talk about groundwater. So, groundwater is the water located beneath Earth's surface. It is stored in aquifers, a rock or soil layers that can store water. So, groundwater is accessed by wells, by digging wells, springs, and underground rivers. Groundwater can be replenished through infiltration, which is the process of rain or snowmelt soaking into the ground and percolating down to replenish aquifers. So number 3, rainwater. It is the most common natural source of fresh water. Yes, rainwater is a fresh water. It is the result of atmospheric condensation and precipitation. Number 4, glaciers and ice caps. So these sources hold the largest reservoir of fresh water, though it is not easily accessed. Water in glaciers and ice caps is frozen water stored in polar regions like North and South Pole and high mountains. Lastly, atmospheric water. So in the air, there are water vapor. It can be condensed into liquid water, and in some regions, in some countries, there are technologies like atmospheric water generators can extract moisture from the air and convert it into drinkable water. So, conclusion, water comes from a variety of natural and artificial sources, each with its unique replenishment processes and availability. Surface water and groundwater are the most significant sources for human use, but rainwater and glaciers also play important roles. Effective management of these sources is critical for ensuring a sustainable water supply for our future generations.
And now, let's talk about the characteristics and properties of water. So water has a set of unique characteristics and properties that make it essential for life and Earth system. So in characteristics, first we have the universal solvent. So ang universal solvent ay it dissolves more substance than any other liquid. enabling chemical reaction and transport of nutrients. So, kahit tulad nga ng dissolved, siya ay nagtutunaw. So, ang water natin ay nagtutunaw. And then polarity. Polarity, water molecules are polar with partial positive and negative charges. So, ang water ay may positive at mayroong negative, kaya nagkakaroon tayo ng hydrogen bonding. So, third is high cohesion and adhesion. So, in cohesion, water molecules stick together due to hydrogen bonding, create phenomena like surface tension, allowing insect to walk on water. So, cohesion. Ang cohesion, ang water natin nagsistick together kasi nga hindi naman siya hindi siya katulad ng solid na napaghihiwalay. And adhesion, water stick to other surface, aiding in capillary action, movement of water through narrow spaces. So, adhesion. So, ang water is parang kumakapit siya kung saan-saan. So, katulad ng glass, tsaka sa plant wall. And thermal stability. Waters has high specific heat, stabilized temperature in organism and the environment. So, ang water ay mayroong high specific heat. So, katulad ng ang water has a boiling point kung saan ang heat ay nagre-reach to 100 degree para masabi siya nagbo-boil. So, and next is transparency. Water allows sunlight to penetrate, enabling photosynthesis in aquatic plant and algae. So, ang water is transparent. So, katulad ng pag nagtutok ka ng flashlight sa water, magkakaroon siya ng diffraction. Ibig sabihin, lilihis lang yung light pero magpapastor pa rin siya. And the other is density anomaly. So ice is less sensitive than liquid water due to the structure hydrogen bonding that forms in open lattice. This ensures ice float in insulating aquatic life during freezing temperature. Next, let's talk about the physical properties of water. So, number 1, state of matter. Water exists naturally as solid, which is ice, liquid, and gases, the water vapor. So, these phases, transition depends on temperature and pressure, making water versatile in supporting life and environment. The next is density. So, water density is at the highest 4 degrees Celsius. Below this, water extends upon freezing. So, this property is vital for the survival of aquatic organism during winter as the water sinks, keeping the deeper layer warm. So next is high heat capacity. So water can absorb or release large amount of heat with little temperature change. So water can absorb. So katulad ng ice absorb heat para mag-melt, and sa release, water can release heat para mag-evaporize ang water. So, fourth is high heat of vaporization. So, water requires significant energy to change from liquid to vapor. So, kailangan niya ng specific heat para maging vaporize yung water. So, next is surface tension. The cohesive forces between water molecule create a strong surface film. This is why small object like paper clips or insect can rest on water without sinking. So, katulad ng ibang animal, yung nagpo-float sila sa water kasi nga hindi sila ganong kabigat and mayroong surface tension, keeping them afloat. So, number 6 is boiling and freezing point. So, at standard atmospheric pressure, water boils at 100 degrees Celsius and freeze at 0 degrees Celsius. This temperature allows water to cycle through Earth's environment effectively. And lastly, let's talk about the water chemical properties. So, first, we have the molecular structure. So, water H2O structure form a dipole moment. So H2O, it means that there are two hydrogen and one oxygen. So partial positive hydrogen ends and a partial negative oxygen end, allowing interaction with a wide variety of molecules. So hydrogen bonding. So each water molecules can form up to 4 hydrogen bonds with neighboring molecules. This contributes to its high boiling point, heat capacity, and surface tension. So reactivity. Water is both reactant and a product in essential biochemical process. So hydrolysis. So ang hydrolysis ay nagbe-break down ng large amount of molecules by adding water. Kunyari, digestion. And dehydration synthesis. So formation of larger molecules by removing water. So nag-aalis naman siya ng water. And pH neutral. So pure water has an equal concentration of H plus or H positive and OH negative ion, giving it a neutral pH of 7. So it acts as buffer in biochemical system. And lastly, electrolytic property. So water dissociate into ions, hydrogen, positive hydrogen and negative oxygen hydrogen, enabling it to conduct electricity when salt or mineral are dissolved in it.
Now that we've explored the properties and sources of water, let's move on to the next topic, which is the reaction of acids and bases in the water.
Let's dive into the world of acid-base chemistry. In these discussions, we look at how acids and bases break apart in water and why pH levels are so important for the health of our lakes, rivers, and also in oceans. We'll explore the basic process that happen when acids and bases mix with water, talk about what pH means, and explains why keeping pH levels balanced is essential for aquatic life. This guide will take you through the key ideas from the basics of acid-base science to real-life examples.
Before we dive in dissociation process, it is essential to know what is acids and bases are. So acids is a substance that can donate protons or the H plus ions in aqueous solution, while the acids is the protons acceptor. According to Bronsted-Lowry theory, which is widely used in chemistry, defines acids and bases in terms of this proton transfer. Acids is the proton donors, increased H plus concentration in water, while bases is the proton acceptors, decreased H plus concentration in water. Example of acids is the hydrogen chloride and sulfuric acid, while example of bases is sodium hydroxide and ammonia. So understanding this fundamental definition is crucial for grasping the dissociation process and its effects on water chemistry.
Alright, let's talk about what happens when acids are added to water. This process is called dissociation. Dissociation, it is when the acid molecule separates into their ions. For example, take a typical acid. When it interacts with water, the reactions look like this. Here, the acids reacts with water to form hydronium ions and the conjugate base. What's important to note it is that these reactions is reversible, which means it can go both ways. The extent of dissociations depends on the strength of the acid. Strong acids like hydrochloric acid dissociate completely and releasing all of their ions into the solutions. Weak acids like acetic acid only dissociate partially and leaving many of their molecules intact.
Let's proceed to dissociation of bases in water. Bases also undergo dissociation when added to water, but differ from process of acid. The bases releases hydroxide ion into the solution, increasing hydroxide concentration. Some bases like ammonia don't contain hydroxide in their molecular form but still produce hydroxide ion through reaction with water. As with acids, the extent of dissociation depends on the strength of the base. Strong base dissociate completely, while weak base only dissociate partially. So for strong bases, we have sodium hydroxide and calcium hydroxide, while for weak bases, we have ammonia.
Now let's simplify the dissociation process into three main steps. Number 1, first, we add the acid or base to water. Second, next, water molecules break the ionic bonds in the substance. And then finally, acid release H plus ions while bases release OH sub minus ions into the solutions. And that's how dissociation works.
Let's move to the concept of pH, or the power of hydrogen. pH is the measure of acidity and the basicity of the aqueous solution. It is defined as the negative logarithm of the hydrogen ion concentration. The pH scales from 0 to 14, with 7 being neutral. Values below 7 indicates acidic solution, while values above 7 indicates a basic solution. Each unit changes in pH represents in tenfold changes in H plus concentration. 0 is for extremely acidic, 7 is for neutral, and 14 is extremely basic. Understanding pH, or the power of hydrogen, is crucial for many chemical processes and biological systems, as even small changes in pH can have a significant effect on reaction and living organisms.
And now, let's talk about why pH levels are so important in natural water bodies. Maintaining the right pH is essential for the health of aquatic system. Most aquatic organisms are used to living in a specific pH range, usually between 6.5 and 8.5. If the pH goes too high or too low, it can have serious effects. For example, in aquatic life, extreme pH levels can mess with cellular processes, disrupt reductions, and in some cases, even cause death in fish and other organisms. In nutrient availability, pH plays a big role in how nutrients like phosphorus and nitrogen dissolve and how available they are for aquatic plants and animals. It also affects how toxic certain chemicals can become. In water chemistry, pH influences chemical reactions in water, including how pollutants like heavy metals interact with the environment. Toxicity often increases when pH isn't balanced. The problem is human activities like industrial pollutions and acid rain can throw off the pH of water bodies. This is why monitoring pH is so important. By keeping track of pH levels, we can protect aquatic life, improve water quality, and prevent long-term environmental damage. In short, pH isn't just a number. It is a key factor in keeping our water bodies and the ecosystems they support healthy and thriving.
With a clear understanding of water's reaction, let us turn our attention to the final topic, which is the water pollutants and treatment.
Good day everyone! We will be discussing water pollutants and the various treatment techniques used to make water safe for consumption. Water is an essential resource for life, but unfortunately, it is often contaminated. So let's dive into the various pollutants that affect water and how can we treat them effectively. So let's start by looking at the different types of water pollutants that pose a risk to human health and the environment. First, aluminum. Aluminum often enters water sources through industrial processes and natural deposit. If consumed in large quantities, it can lead to neurological disorder like Alzheimer's disease. Second, ammonia. Ammonia contaminates water through agricultural runoff, sewage, and industrial waste. It is toxic to aquatic life that can indicate poor water quality, leading to harmful bacteria. Third, arsenic. A natural occurring toxin, arsenic can contaminate groundwater, posing serious health risks such as cancer and skin disease when consumed over long periods. Fourth, barium. Barium enters water sources through natural processes or mining. Prolonged exposure can cause high blood pressure or kidney damage. Fifth, cadmium is a toxic and can leach into water supplies from industrial runoff. Long-term exposure can lead to kidney damage. 6. Chromium. Chromium, especially hexavalent chromium, is carcinogenic and can enter water from the industrial waste. It increases the risk of lung cancer and liver damage. 7. Copper. Copper can leach from corroded pipes, leading to gastrointestinal issue and liver damage if consumed in large amounts. 8. Fluoride. Fluoride is added to many water supplies to prevent tooth decay, but excessive exposure can lead to dental and skeletal fluorosis. 9. Bacteria and viruses. Contaminated water can carry bacteria and viruses that cause diseases like cholera and hepatitis. This is often the result of poor sanitation practices. 10th, lead. Lead contamination from old pipes and plumbing fixtures can cause developmental issue in children and kidney problems in adults. 11. Nitrates and nitrites. Nitrates, primarily from agricultural runoff, can cause blue baby syndrome in infants and increase the risk of cancer with long-term exposure. 12. Mercury contamination. Often from industrial discharges, can accumulate in fish, causing neurological damage and kidney failure for those who consume contaminated seafoods. 13. Perchlorate. This chemical, found in rocket fuel and some fertilizers, interferes with thyroid function and can affect infant development. 14. Rhodium. A radioactive element, rhodium can naturally contaminate groundwater and lead to bone cancer or leukemia with long-term exposure. 15. Selenium. With essential in small amount, excess selenium from mining and agricultural runoff can cause poisoning with symptoms like gastrointestinal distress and nerve damage. 16. Silver. Silver contamination in water usually comes from industrial waste. High level of silver can cause a condition known as argyria, where the skin turns a blue-gray color. And the last one, uranium. Uranium is a radioactive metal that can contaminate groundwater, potentially causing kidney damage and cancer over time. Now that we've identified the pollutants, let's explore how we can treat water to remove these contaminants and make it safe for consumption. First, pre-treatment, or the coagulation, flocculation, and sedimentation. Coagulation. Coagulants such as aluminum sulfate are added to destabilize particles in the water, making them easier to remove. Second, flocculation. After coagulation, the water is stirred to form flocks, which are larger aggregates of contaminants. And the last one of this process is sedimentation. These flocks then settle at the bottom of sedimentation tank, separating out from the water. So this process reduces suspended solids and prepares the water for further purification. Second process, screens. Screens are used to intake stage to remove the larger debris like leaves, weeds, and larger particles. This helps to remove the equipment downstream to reduce the load on the later treatment stages. Third process, gravel filters. Gravel filters use layer of graded gravel to filter out turbidity, algae, and suspended solids from the water. As the water passes through the gravel, particles are trapped and removed, leaving cleaner water behind. Fourth process, slow sand filters. So sand filtration uses a layer of lime sand to filter out suspended particles, algae, and microorganisms. This is an effective method especially for small-scale water treatment system and uses both physical and biological processes to purify water. Fifth process, activated carbon. Activated carbon is highly porous materials that absorbs contaminants from water. It is effective at removing organic compounds, chlorine, and particles that cause bad taste and odor. It traps contaminants on its surface, improving water quality. Sixth process, aeration. Aeration introduces oxygen into water, helping to remove gases and volatile compounds like hydrogen sulfide. This is typically done through methods such as pack towers, aerators, or diffuse aerations. Seventh process, it is membrane process, reverse osmosis, ultrafiltration, microfiltration, and nanofiltration. First is reverse osmosis. Reverse osmosis uses a semi-permeable membrane to remove up to 99% of dissolved contaminants including salt, metals, bacteria, and viruses. Second is ultrafiltration. Ultrafiltration membranes remove larger particles and microorganisms while allowing smaller particles like salts to pass through. And third is microfiltration. Microfiltration removes larger particles and microorganisms, but it is less effective than ultrafiltration. And last is microfiltration. Microfiltration membranes are finer than ultrafiltration and can remove certain ions and small particles. And the last one process of treatment water contaminants is distillation. Distillation involves boiling water to create steam, then condensing it back into liquid form. This process removes bacteria, pathogens, and larger contaminants, but it doesn't eliminate ionized gases or dissolved ions. And that's all the processes or the how can we treat water contaminants. So, in conclusion, water pollution is a serious issue, but with the right treatment technologies, we can remove harmful contaminants and provide safe drinking water. The combination of pre-treatment processes, filtration, aeration, and membrane technologies, the distillation ensures the water meet the necessary standards for health and safety. As we come to the end of our presentation on the chemistry of water, first thing first, water is truly at the heart of life, science, and sustainability. By understanding its chemistry, we not only gain knowledge but also a responsibility to use and manage it wisely. That's all. Thank you for watching this presentation, and I hope you are inspired to learn more about water and its vital role in our world. Thank you!